My name is Yun, and the topic today is universal outlier hypothesis testing. So basically, the problem we're looking at is we're trying to identify outliers among typical data streams. So as we can see in this picture, we have M data streams. So every row here is a data stream. So the outliers are actually in red, and the observations in those outlier streams, they follow a different distribution. We call this outlier distribution, which is different from the typical distribution that generates all the observations in the rest of the typical streams. And basically, our goal is to identify outlier streams with a certain level of accuracy, using as few number of observations as possible. And we're mainly interested in the universal setting of the problem, where we don't know anything about the typical and outlier distributions. And there's no training data, so we don't have any training data to learn these distributions beforehand. So we use S to denote the set of outliers. And we assume the size of S is at most K, and K is known to us. And we use mu to denote the outlier distributions, and pi the typical distributions. So as I said before, we're interested in the universal setting of the problem. So we assume like mu is not equal to pi, and they have full supports over a finite alphabet. And that's the only assumption we know about mu and pi. So here is an example of this situation. So here S is equal to 1 and 3. So the first and the third sequence, they're outliers. So the observations in those two sequences, they follow a distribution mu. And the rest of the observations, they're generated by pi. And we assume, within each sequence, the observations are ID. And every sequence is independent from each other. So basically, if we know mu and pi, we can write down the likelihoods of all the observations. So under the null hypothesis, because every observation is generated by pi, so basically only pi shows up in here. So the inner product is basically the likelihood of the kth observations of all the sequences. And the outer product comes from the independent assumption between the observations. And under every non-null hypothesis, we can also write down the likelihood function of all the observations. So S here denotes the set of outliers. So when I is the index of the sequence, is in S, Y sub k superscript I is distributed according to mu. And if J is not in S, meaning J is actually, sequence J is one of the typical sequences, so it's going to distribute it according to pi. So that's why, so that's the inner product here, the parts within the brackets. And then the outer product comes from the independent assumption between the observations. And we use L to denote the likelihoods. And obviously, it's going to be a function of both mu and pi, and also the underlying outlier subset S. So we actually consider two different settings. So one is the fixed sample size setting, and the other is the sequential setting. So for the fixed sample size setting, we always take, say, like n number of observations before we stop and make a decision. But for the sequential setting, we have the freedom of either to stop and make a decision, or if we're not confident enough, we can always take more and more observations until we're satisfied. And we proposed two tests, each for a different setting, respectively. And we analyze the performance of the tests, and we show these tests are exponentially consistent under all the non-null hypotheses, and consistent under the null hypothesis. And we also have some simulation done, like just to evaluate the performance of our tests, both on real data and simulated data.